Okay, let's keep going with this idea. We'll sketch x equals u, y is equal to v. Oh, okay, not much is going on with this parameterization so far. If each of the parametric variables is just one of the standard coordinate variables, but z is equal to u squared root u squared plus v squared, and we'll have u. Here's some changes. Okay, we'll go between two constants, -7 and 7, but v will be bound to be between negative root 49 minus u squared all the way up to positive root 49 minus u squared. Now, what curve is this? This is actually still the same cone that we just saw a moment ago. Okay, I want you to think about how if all you did was you substituted x for the u's and y for the v, then you just have z is equal to root x squared plus y squared. And this should really end up just being the same cone before we started modifying it by shifting and stretching things and so on. So just for a quick drawing of it, should be the same cone that we had a moment ago. That should be a z-axis there all the way up to 7. 7 here on the y-axis, 7 here on the x-axis. Same shape, but here's the thing. But the parameter domain is quite different. So what's the shape that we're going to draw on the UV plane based on the information that's right here? This is actually going to be this filled in circle here, of radius 7. So the parameter domain that we saw in our earlier example was a rectangle, and here we have a filled in circle instead. Okay. This, by the way, if you'd like to say it this way, this is the graph, just to help convince you of what's going on here. This is the graph of g of x comma y is equal to root x squared plus y squared. If you're not so certain about this, why not just take the data that's provided here and go put it into that parameterization app. The main point of providing this example, though, so we're done with the example, but the main point of this is to say that there are multiple ways of parameterizing the same surface. Okay, and I don't mean just multiple ways like there's some real obvious things like just switching the roles of u and v. Okay, there's something more like what we're seeing here where the parameterization here is fundamentally different than the one that we saw, yet in the end we get the same shape. And you'll see this kind of thing a lot. So for parameterization of surfaces, there's really a lot that goes into some ingenuity of how you view things, what you see first, and things like that. Obviously, for starting though, you're just providing a lot of examples so that you can just see what some of the thought processes and motivations are in building up parameterization of a surface in the first place. But you've got to get real comfortable with this, and please go back to the examples we've looked at, revisit them over and over, use the grid curves to help. Now let's explore our way towards building towards something. I hope this line of reasoning is going to be helpful. Let's consider the parameterization, the following parameterization. Back, we could have seen this very early in the semester. So x is equal to 2 plus 3t, y is equal to -1 plus 4t, and then z is equal to 3 plus 5t, and t goes between 0 and 1. Okay, you'll notice we're back to just t. We don't have two parametric variables or two parameters. We don't have a u and a v. We just have one variable called t. Now, what shape is this? This should be very recognizable what kind of shape this is, right? Just based on how the parametric equations look. Yeah, so this is, of course, a line segment from the point 2, -1, 3 to the point 5, 3, 8. Now, the thing is, we could also say that what this is it's a line segment, but you can start from the point 2 comma negative 1 comma 3, and then you move along the vector, well, 3, 4, 5. And then when you've moved fully along the length of that vector once, when t is 1, that's where you stop. Now, this view is a bit more geometric. If you start at a point, maybe, okay, we're just going to try to fake the picture up here a little bit, but there's this point 2, negative 1, 3, and then, there's this, from here, there's a vector 3, 4, 5. So there's a copy, there's a vector 3, 4, 5, just not situated at the origin, and you end at this point here. Okay, maybe I'll try to get the labeling of the vector not so close to the ending point. And so then t equals 0 gives you that point, t equals 1 gives you that point, t equals 0.75 gives you that point, and so on, right? So you move along the vector. And it's a much more geometric view to say it in this kind of language here, and it'll help us with the next example we're going to take a look at. So I'd like to describe the following parameterization. X is equal to 2 plus 3u plus v. Y is equal to negative 1 plus 4u plus 5v. And then z is equal to 3 plus 5u minus 2v. I'd like you to, before we do anything else, just notice how similar this part is. That is the x equals, y equals, z equals parts where you have a constant plus a number in front of u, and look at how similar that is to what we had before. Just all the t's became u's, yeah? And then let's describe the bounds here. We're going to have 0 less than or equal to u less than or equal to 1. We're also going to have 0 less than or equal to v less than or equal to 1. So in trying to describe what shape we're going to get here, let's try to relate it back to what we just saw about parameterizing a line segment. Now, punchline, this is not going to be parameterizing a line segment anymore. There's two variables going on. There's two different sort of directions of movement, if you will. Now, here's the thing. Let's just go with if v is equal to 0. Let's just, for a moment, fix v equal to 0. In other words, in words, let's describe the grid curve for the situation of v equals 0. Then, u ranging between 0 and 1 is really this, right? It's what are we looking at here? We would start at the point 2 comma negative 1 comma 3 and move along the vector 3, 4, 5 as we had just drawn a picture of up there. Okay, but now let's think about the following. What if u is equal to 0 now? So instead of fixing v equal to 0, let's let v vary and let u be fixed to 0. Then, as v takes on values between v takes on values between 0 and 1, then we start again at the point 2 comma negative 1 comma 3. But now we move along, well, what vector? Can you see it? Based on the information we have, shouldn't it be 1 comma 5 comma negative 2? Right, based on the coefficients of v. So now, think about what would be happening. What if, so what object are we going to get when we allow both variables to vary? So what object would we get if u and v both vary between 0 and 1? So you've got to really think about how, starting at this point, changing the value of u means how much of this you add, what proportion of that vector that you add, and then changing the value of v is starting here, and then what proportion of this that you add. So it's all about how much do you move in this direction, and how much do you move in this direction, and they're completely independent because u and v can both be 1, right? Or u and v can both be a half. Okay? So the object we're actually going to get is a parallelogram. Let's go ahead and go take a look at it. Okay, well, here's the object. I've already typed in the parameterization. This is the original point over here. This is 2, negative 1, 3. And then the grid curve for u equals 0 is shown in blue. So if you just pretend the v, so yeah, pretend the u, yeah, let's see. Let's actually look at the grid curve for v equals 0 first. So if you pretend v is 0, so all the points that are shown in red on this, it's one of the edges of this parallelogram, just pretend this plus v is gone, the plus 5v is gone, the minus 2v is gone, because v is 0, right? So then as you move along this red curve from this point to that point, that's parameterizing a line segment. Now instead, if we look at the grid curve where u is equal to 0, then there's a parameterization from the line segment that starts here and ends there. The point is that we're allowing both u and v to vary. So if u is 0.45, we're talking about all the points that are here. If v is, say, 0.75 right there, so this, right where there's a parallelogram, we can kind of see it a little more head on, if I guess maybe from the back over here as well. Let's look at it from over here. So u is approximately halfway, right? And then v is 3/4 the way, and so you get this one point where the blue curve and the red, well, they're both line segments, where the blue and the red intersect. On the yellow, there's just a single point right there. And actually, when they're both equal to 1, you get the opposite corner of this parallelogram from when u and v are both 0 over here. Now, let's take this and modify this slightly and talk about what shape we should get. Okay, we're going to just change it up a little bit by not having u and v have bounds of 0 to 1. That's the only change we're about to make. So, to tweak it, what should we expect if we just change u to go from -2 to 2 and v to go from -2 to 2? What should we expect when we look at the shape over here? Okay, so if we change u, now keep in mind the values of u, oh, there we go, I thought the app had frozen. Here's what we get up to u is equal to 1. So imagine what will happen if we change this to be a 2. And now it's just a bigger parallelogram, isn't it? If we change v to be 2, does that make sense? V equals 1 was right there. Now we can go up to v is equal to 2. And then what if we change u to start not at 0 but at -1? And then to start not at -1 but instead at -2. Okay, it's kind of spilling a little bit. I could zoom out so that it doesn't get cut off by the bounding box. Same deal. V, instead of starting at 0, how about at -1? And then v starting at -2. So we should really, in the end, zoom out because it's getting cut off. We should be seeing just a larger parallelogram that should still have the same normal vector when we do this. Okay, so we got that. Now let's change this. So we just saw that would be a larger parallelogram. But let's now take this, tweak it a little further by doing the following thing. What if, instead of u being restricted between -2 and 2 and v being restricted between -2 and 2, now we just say that u and v belong to reals, the set of reals. So u and v can be any real numbers you want. Then what object should we get here? Instead of a parallelogram, so this is just a larger parallelogram than the parallelogram we had earlier. But now we should end up just with a plane, right? If there's no more bounds. Now we unfortunately, using the app, cannot mimic. We cannot actually do this. We can't just, the way this has been programmed anyway is that u and v both need starting and ending values. So we'll just kind of simulate this by just choosing -100 to 100. And the point is then we really will get a plane. And so I'll just keep zooming out. You see that, eventually we'll run into some trouble doing this, but I hope that's a decent simulation that we ought to be getting a plane for this.